Now we just need Jim to come up.
All right, hi everybody. I am Jim Cowie from DYNE. This is my very first DNS OARC. And so yeah, thank you. Thank you. It's kind of like Nanog, except a little angrier and a little smaller. So that's good. I feel at home. Yeah, I came over to DYNE with the Renesas acquisition, and a lot of what you'll see today involves the DNS through a performance lens, perhaps. And it's a sneak peek at a project that Joe Abley and I, now I'm fortunate enough to work with, have been doing this year, poking around particularly the ccTLDs of the world to try to figure out what information is lurking in the zone files that might be interesting. That's kind of a great research topic. And this is the sort of lens that I talk to people about when I take this topic to them, is that the zone files actually, the TLD zones have a great amount of information about locality. So they are in some sense local, right? They belong to a country. But their contents are spread all over the world. And what we can use them to do in some sense is to say, if you think of a zone like .ca as being distributed, where is it distributed? How is it that the content which is made here and hosted here and consumed over here kind of flows, almost as if you'd think of it as import-export. Let's dig into these files and figure out what kind of information might be lurking in there that the zone operators could actually contribute to people who are trying to make policy and think about things like economics or the evolution of the internet or fragility or resilience or all the things that we know are good but they're just learning about. So here's what we did. We said a zone, basically a big one, is a map. What can we learn from the map? What's the simplest experiment we could do? So we did two different kinds of experiments. We started with one, which you'll see is based on the published popular sites, the top Alexa sites, which form kind of a pseudo-zone for each country. And then we did it for real with some ccTLDs. And we'll talk today, thankfully, about .ca, which we were fortunate enough to share invisibility into. So real quick, because it doesn't really have DNS content, but it's a nice precursor to the next experiment, taking a look at the Alexa 100. Okay, we all know that the Alexa 100 are not a great proxy for popular content, but they're available. We can use them. We all kind of know what that means. So we did that. For various countries, we took the top 100 sites. We simply resolved them to A records, hopefully from inside the country. And then we geolocated. We pulled up the old BGP data to figure out who originates that content, who's providing transit to that content upstream, and so forth. And we calculated a local hosting fraction. And so you get to do something like this. So here, every dot is a country, and the size of the dot corresponds to the amount of IP space they've got in the table. The vertical y-axis is the number of autonomous systems in that country, in being something roughly meaning at least 80% of their on-net customers are in that country. And then the x-axis is the important one here. It represents what percentage of their Alexa important sites were actually hosted in the country where they are popular. And so it's interesting because it clearly does correlate. As your country grows to include more autonomous systems, there's a rank order correlation of maybe 0.69, so not nothing, but not certain either. But it leads you to say that as you get more autonomous systems operating in your country, you kind of naturally attract more of your content home. You are more successful at specifically getting people like Akamai and Google and so forth to come and put stuff in your country, which increases your local hosting percentage because that counts. You can see roughly that people on the left are kind of like importers. They have too little local hosting for their size. The people on the right are exporters, like the US or SIEN. We host other people's stuff. And you'll see that Canada and Mexico, I don't know if this will work, but Canada and Mexico are the purple dots on the left. They tend to be pushed a little bit to the left, mostly because they're right next door to the US. And that forms a really tempting place to host content, which may be a reasonable way to give people a good experience, but that's what we wanted to figure out. So if we just break it out, red here means it's in, this is for Canada specifically, the top 100. If it's blue, it means there's at least some of that content here. And if it's red, it means it's somewhere else. It's probably the United States. The right-hand column, just because while we're looking, we should look, is whether or not they have IPv6, right? So there's too much red here. And if we go into the next section, next 48 or so, it gets maybe a little better on the domestic side, right? There are great .ca sites here that are hosted in Canada. There's still a lot of red. If you add it all up, there's only about 16% of those Alexa sites that end up with some IP coverage in Canada, adding up partial percentages. So if a site has, some people tell us it's in Canada, some people say it's elsewhere, we apportion that appropriately. And remember, this is just the top-level domain. If you do it for www, you get kind of the same answer. CDNs obviously are at work making this picture better. This is not how content really is delivered to consumers. But as some sort of an easy metric to calculate, just these top-level domains, 16%. Well, let's do it for the DNS folks. So fortunately, we were able to do some cooperation with Sierra. And when we look at .ca, we wanted to take a look at the entire zone. We did it a few times over the course of the summer and found that the statistics that come out of this process are really very stable, which is as you'd imagine, because .ca kind of grows at its leading edge but is strongly conserved inside. And we went ahead and took all of these NS records, toted up all the servers in there, and just resolved the apex domain against those servers. And counted, did the geolocation, did the BGP analysis, and just wanted to find out what would it look like. And remember, Joe and I had been doing this for sub-Saharan Africa initially, where if you take a look at the .ccTLD for an East African country, they'll have very high percentages overseas, and it will cost them a lot in terms of latency to reach that traffic. What would we see here? We didn't know. One thing that was interesting is that the top servers who are authoritative in the zone are clearly Canadian, right? There's a great Canadian focus to that. But then when you actually ask them, where are these things, it comes out to be someplace else, as you'll see. While we were asking, we said, what other kinds of questions might we ask? And we said, well, as long as we're asking, let's find out how many of these will actually give you a public key back if you ask. It turns out to be about 0.16%. Right, so 99.84% of everybody out there just doesn't give an answer. And what was stranger to me, although it was later explained by some of you, is why there are actually far fewer delegation DS records in the .ca. Right, so even though people have a public key, you don't even see a DS record upstream, which is, perhaps it's a topic for conversation later, what would make this easier to get these things into .ca. And there's nothing particularly shameful here. I think this is kind of what you see as you look across many of the TLDs, and even in COM. It's just a very small percentage of these things that are actually signed. And unfortunately, it's kind of similar to the proportion of these domains that actually will return you a quad A if you ask. So, but again, this is a digression, because what we mostly came here to talk about was performance. And performance means geography and latency. And so here's the actual number. So remember, in Alexa land, it's about 16%. In .ca, you expect it to go up, because these are smaller domains. There's a higher chance, one would think, of these things being hosted in country. And in other smaller countries we've looked at, that is the case. The local ccTLD will have massively higher local hosting of the domains in the zone as opposed to the stuff from Alexa. Here it's a little better. Okay, so 18.7%. But the big red Pac-Man is there. It's almost all US, which is what you'd expect. If we took a look then in BGP at who is originating the IPs that come back, the top origin providers worldwide skew towards the US, and in particular, the distribution skews towards just a few who are, for example, GoDaddy, which turns out to be, geolocates to Arizona. It's huge numbers of parked domains. So clearly, utilization in the zone is never, flat. Some of these are heavily used. Some of them are just have been sitting there with dust on them for a long time. And there's a very, very long tail. I mean, it's amazing that the top few providers for origins here have double-digit percentages, but then this goes on for thousands of providers. If we focus on just what's hosted here in Canada, you get this list, which of course is a different origin list. These are true Canadian origins, despite the word USA in Peer 1 Network's registered name. It really is, it's local hosting here. And if we break it out by province, you can see that Ontario is about 2-to-1 over British Columbia and Quebec. Everybody else kind of fits into the remaining 1.7% of the total zone. So you get kind of this three geography game going on. If we take a look at just who's originating the traffic in Ontario, right? So these are answers that came back. We geolocated those to an Ontario provider. It looks a lot like the Canadian distribution, as you might expect, since Ontario is the largest provincial share. But something interesting happens when you go to Quebec. Almost a completely different spectrum of providers, and these are well-recognized, local, largely Montreal-based providers. And so clearly, the language difference drives content difference, which drives hosting difference, and in this case, geographic locality. So people who are getting Quebec content in Quebec are getting better performance in some sense because their providers, their origins are more likely to be in this city. If we go upstream and look at transit providers, right, because we know the A records, we know the IPs, so we know the origin providers, so we can look in BGP and find out who is selling them IP transit. You get some interesting rankings, and they are different between Quebec and Ontario. So in Quebec, Tata comes out #1, as you might guess, because everybody loved Teleglobe back in the day, the Crown Corporation that eventually turned into Tata or was merged in. #2 is kind of surprising. So level 3, so both Tata and level 3 by our count have more than 90% of the Quebec content on net with them. And level 3 is not particularly sort of #2-ish in the transit rankings for Quebec. So it's illustrative of the fact that you can, because the distribution of hosting is so skew, that there are a few providers who have a large share of the domains. By selling to them and having them on net with you, you can actually rise higher in this ranking than you can on a generic IP wholesale transit ranking. So, why did we care? Well, we wanted to find out, in some sense, how we could talk about the impacts of locality and content as seen through the zones on end user experience. And here's the elephant in the room is the US-based hosting of the Apex domains here. So remember, 78% are hosted in the US. So there's a few single companies in a few cities that were responsible for large chunks of this. So GoDaddy in Phoenix, Endurance in Boston, Amazon in, I think it's Ashburn, or the DC area, and Unified Layer in Salt Lake City, right, are pulling down huge percentages of this zone. And then there are other markets here that are also substantial, multiple percents, but there's a longer tail of smaller hosting providers that are present. So we said, let's take a look at latency. So this is the DYNE global measurement infrastructure. It's a bunch of physical and virtual servers around the world from which we run traces and do ICMP-based round-trip measurement to a panel of about 1.5 million IP addresses, and we try to spread them through all the prefixes and so forth in every market with every provider. And we look back and take medians over given look-back periods to figure out sort of what a characteristic time might be between two geographic locations. And we can either do that in a provider-independent sense, or we can do it in a provider-specific sense. So here, let's take a look at it in a provider-independent sense. So we take all of the measurements, perhaps, that we took out of Toronto over 7 days and take the median latency for all of the IPs in our target set, which happen to be in these particular geographic markets. And we've colored the dots here so that you can see what a typical performance looks like. And it kind of matches your expectations, right? You see these contour outlines of where you can get 50 millisecond round-trip performance from Toronto. Lighter green is up to 100, and it goes up through the temperature scale until on the other side of the planet you're at 350 plus. And Toronto does really well. There's a reason why Eastern Canadian content can be easily hosted in the Eastern United States. The latencies are reasonable. If we actually carve into the same data and start looking at the dispersion of results over the United States, this is what you see, right? Within the Toronto region, obviously you're getting less than 10 milliseconds to content there. If your things were hosted elsewhere, it's going to be 17, 18 milliseconds in Montreal. It's going to be maybe 22, 25 if you're in the major markets of New York or Ashburn. And then from there, it actually goes back up, because if you're trying to serve content, let's say to anybody in the Northeast United States, it's going to go to these major markets and come back, most likely. So Boston's going to be 30, Rochester, New York, right over the line, right? It's going to be 31. You get 35 to 37 throughout the US, the American South. If you're trying to get to, let's take it the other way. If you were hosting content in Texas or Arizona or Los Angeles or the Bay Area, then from Toronto to a Toronto consumer, it goes up and up, right? It goes up by, well, as you'd expect. It's basically speed of light, right? Because this is a median over all providers. Using the traditional routes, this is kind of what you get. And if you flip it around now, you can look at Vancouver. So Vancouver is the same map with east-west reversed. They're faster to the US West, they're slower to the US East, kind of as you'd expect. And again, if you dig in, it's interesting that Vancouver's latency footprint extends to Seattle and Portland very nicely, less well to San Francisco and Los Angeles. So you're paying basically a 3x latency penalty if your content is being hosted in the Bay Area, as opposed to hosting it right there in Vancouver. And you shouldn't even starting to think about hosting it in Arizona, up to 53. Go to host it in Houston, it's 72 milliseconds. Host it in Miami, it's 94. Havana is on there, that's 194 milliseconds, so don't do that. But people do that, right? Because they think about price first, they think about convenience maybe second, and then they stop. And if they kept going, they would have thought about latency and location and so forth. We can ask ourselves whether it really matters, right? I naively went into this assuming that most of the content for .ca was consumed by Canadians, but in fact, if we look at a sample of the resolvers who come asking authoritative questions against .ca, you actually see a distribution of recursives coming that is not Canadian. It's all over the world. Everybody wants .ca content. And in fact, Canada comes in about 7% of the resolvers who ask questions, and the US being 27%, and Brazil being 8%, counting resolvers, not counting queries, right? Because that is its own strange distribution. So that's one of the insights here, is the puzzle is if you were to optimize this, you're trying to optimize for the Canadian audience, but you're also trying to optimize for the global audience who wants Canadian content. So if I'm going to, too long, didn't read this. The basic points are, one, if you are trying to serve a Canadian audience and you've got a choice and you choose to host your stuff in the US, you've given yourself a 2 or 3 or 4 or 7 times latency penalty over hosting it at home. It's kind of obvious, right? Now that's a multiple. The actual increase in latency may only be 20 milliseconds, 30 milliseconds, but that's a huge multiple of being able to get less than 10. Turn it around, all the people in the world who want to see Canadian content are coming here, and they're getting 150, 200, 250 millisecond latencies to content. And so they don't care if it's hosted in the US or Canada. So why shouldn't it be hosted in Canada, right? That's the basic analysis. You can improve things for the Canadian consumer by moving content closer to home, and you're being indifferent, basically, to the outcome for everybody else, because frankly, there are cables that land in Canada as well. So I'll wrap up. I know that we're right at the end, but this is kind of why we undertook this. And this is you're seeing early stages of this and the very first sort of simple measurements. But as we look at zones, I'll be doing the same kind of analysis, fortunately it looks like, in Moscow in December for .ru and for the Cyrillic version .rfa. And we should be finding out some very interesting things about where content is hosted for those, whether it's being kept domestic or overseas. That'll be at the Moscow Peering Forum. But this is what we want to know. We want to say, what are the trends? Is local hosting on the rise? Is it going down? I hear a lot of talk about people who want to bring content home and repatriate content. Is it actually happening? What's happening to DNSSEC adoption? Not like at the level of the big zones that we can all take care of, but actually out at the edges. And what's happening in terms of actually V6 penetration? And these are the questions. What we're going to look at, especially in some place like sub-Saharan Africa, is as exchanges open up, as cables come ashore, as the market changes, as new providers appear, what happens to all these latencies? And what happens to the shift of the choices people make, where they decide whether to host it abroad or domestically? That's it. I think if I were going to look at this again, I think I'd want to come back and take a periodic look, because these zones grow like geodes. You know, they have strongly conserved content at the core and then a fresh, interesting set of deltas at the edge. So we need to come back to this probably quarterly to see what's going on. And again, it's very interesting to take a look at the locality trends in the audience, not just in the content that's being hosted. And finally, thanks to Sarah for letting us take a look at this. And if you have any pull with anybody else who might like to take a look at similar analysis for their country, of course, let us know. All right, I'll stop there and take questions. The politeness of the mic.
David Farmer, University of Minnesota. You kind of stole my question. That was, what about exchange points and the effect on them? You sort of said that's future. Anything you can say about that now?
I can restate sort of the obvious, maybe it's not obvious. It wasn't obvious to me until I realized it was obvious, that local content measured broadly, meaning not just the real local hosting providers, but also the Akamais and the Googles and everybody else who comes to help with that. As they pile on the train, the local hosting percentage starts to jump up. And that's kind of a leading indicator, we think, of a market that obviously some large content providers are going to vote on being worth investing in. So if you see the local hosting go up, it means you're doing something right from their perspective, which is great validation. And then hopefully that's the sort of validation that allows you to talk to local providers and maybe the incumbent and have them come in and appear at the IX. It's kind of circular, you know, what's signal and what's side effect.
Can you go back to the Alexa 100 slide?
Sure.
Up, that one, yes.
The top one.
Anycast has some impact.
It does, yes.
I know the addresses that my employer Cloudflare uses. They're either called, depending on which block we're called US, Hong Kong.
Yep, absolutely.
And I see on this list 2 or 3 customers that I know of. I know we provide IPv6 for all of our customers, and we have Anycast node in Canada.
Yep.
So why are they only showing IPv4 only, and why are they showing up as foreign?
I don't know. I can dig in. You can come back and give me some domains, and we'll go see why we didn't see a quad A when we asked for it.
Okay.
Paul Hoffman, I actually sort of wanted to focus on your second to last slide when you were talking about you were going to go do this again in Russia. When you do that, I know you said this is December, so that might be awfully soon.
Yeah.
Boy, would it be really cool if, we all could see those afterwards, especially for the IDN stuff, you know, bringing it back to DNS stuff.
Yep.
But if you have any spare time, if you can do some, you know, just as you were talking here about Canada and the United States, Russia is the equivalent of the United States for a lot of its neighbors, many of whom who have IDN, CCTLDs as well.
Right.
If you could do any of those analyses as you're doing that, boy, would that be cool.
I'm reaching out now, and we're trying to talk to Kyrgyzstan and some of the folks in that region who absolutely, they are the Canada to Russia's US.
Right, exactly right. And especially on the IDN stuff, because a lot of them, in fact, I mean, Canada, of course, can't really use an IDN, but a lot of them are very heavily, are surprisingly reliant on their IDN equivalents already. So I would really like to see if you can be doing some analysis on that. Thanks.
Absolutely will. And .RFA is much larger than I thought, which is great.
Matt Poundset, right side. What I was going to say actually is a bit of a, might be an answer for Oliver. Speaking as somebody who has run Anycasting stuff worldwide, we found that anycasting from anywhere in the eastern US and in Toronto, the same blocks, the traffic goes to the US by like 90% of it.
Yeah.
And it seems to be, the reason seems to be a combination of BGP shortest path and the way a lot of Canadian ISPs route and peer. The reluctance of certain ISPs to peer in Canada just means that traffic goes to the US first, and therefore those sites are closest.
Yep. Anycast not matching geography is a clear sign of something at ill with peering. I would refer you obliquely to the last blog that we published on Dyn Research, which talks about an instance of K-route which sneaked out of Tehran and became visible in India, despite being 4 times AS path prepended and clearly not a desirable route for anybody, and yet it got chosen because in India, peering is kind of funky.
Jacob Zach from CIRA. Good work on the presentation and the statistics. One point I do want to make, I believe when Dyn did the research and analysis on the authoritative CA zone that you guys are secondary anycasting for us, it didn't include stats from CIRA's own Anycast clouds and or other Anycast providers. CIRA is at, I believe, 7 or 8 Canadian internet exchanges, and therefore I do believe that the breakdown of queriers is likely higher than the numbers might have reflected because we are so fast to the various regions in Canada, given our Anycast at the IXs.
Yep. I was not eager to over-specify our relationship, but I think your analysis is correct.
Randy Bush, IJ Cryptech. 2 things. It's not that the ISPs here are schmucks. It's that the cost going south to the States and going across and coming back up is radically less.
Yeah.
What you're seeing is heavily tilted by, funny enough, dollars. Both countries use it, just different dollars. Yep. The second thing is on that interesting study of Tehran, you'll find I think a much more considered analysis and deeper analysis published by Ripe Labs shortly thereafter.
I would echo that everybody should go read Emil's blog. They used the Atlas data to take another perspective on what we did, and it was quite interesting. Have we reached the end? Very good. Thank you again.
Thank you, Jim. Next up, we have Martin Willink, hopefully I didn't butcher that too badly, talking about DNS Big Data Analytics. Is it? Disconnected. Okay, this is heavy.
Okay, hi everybody. I'm Martin Willink, so you did just fine. I work for SIEN, and I would like to share with you a little bit of our experiences in setting up a big data analytics platform. So first, a little bit about SIEN for those of you who don't know. SIEN is the domain name registry for the .nl ccTLD. Currently, we're running a little bit over 5.6 million domain names, and the cool thing is that almost 2.5 million of those are secured with DNSSEC, making it, I believe, the largest DNSSEC deployment in the world. And our labs team, SIEN Labs, has been working on this system for at least the last year and a half. Well, if you look at data at SIEN, it mostly is DNS data, and we see about 3.1 million unique resolvers each month. And Together, these resolvers send us about 1.3 billion queries each day. If we were to capture all that data and store it as compressed PCAPs, it would be about 300 gigabytes of data. It's not huge data, but for us, it's pretty big. So in order to be able to analyze and at least store and analyze this data, we wanted to develop a system that could do that with the goal, the stated goal would be to improve the security of .NL and security and stability of .NL based on empirical facts derived from this data. Well, the first problem we faced was that the existing tools you can use to analyze data captured on the network, like PCAP data, don't really scale up really well if you have lots of it. So we started looking around for other solutions, and our main requirement for a new solution was that we wanted to have a high performance, near real-time data warehouse. It doesn't have to be like millisecond response times, but we would like to have some like interactive possibilities that an analyst can type in a query and get a response within a few seconds or a few minutes, but it shouldn't have to take hours or days to analyze large volumes of data. Well, the approach we took was that we got rid of the PCAP data, converted it to a more performance-optimized format, and used tools that leverage the capabilities of that format in order to get a better performance out of the system. So we came up with a few requirements. I think the most important one is SQL support. We have a lot of SQL knowledge at SIEN. So any system that would support SQL would be easily adopted by the new users. And if you didn't have SQL support, we need to add or offer additional support for the new users, or even have dedicated programmers, depending on the API of the new system, to be able to analyze the data. And scalability, of course, very important. We want to start small, prove its value, and then be able to scale up when we add more data. Performance also critical. Yeah, as I mentioned, preferably it should be somewhere in the neighborhood of interactive querying. The capacity of the system, yeah, we would like to store at least 1 year worth of data and also be able to analyze it, because storing is only one part of the question. And also, we don't want to lock in the data in a particular database system where the data can only be queried through that one engine. We want the data to be available, to be used by multiple query engines if possible. And yeah, also, yeah, that was not my requirement, but please don't spend too much money on this. So when we started looking around at what stuff is out there, what can we use to build a system to store this data and analyze it, we looked around and evaluated a couple of SQL and NoSQL solutions. Well, a lot of them are pretty known, like the relational SQL database, and we looked at PostgreSQL, looked at MongoDB, Cassandra, Elasticsearch, some of you probably know all these. We looked at Hadoop combined with HBase and Apache Phoenix, which is a SQL layer above, which you can use in combination with HBase. And we also looked at what we call SQL on Hadoop, which is a combination of Hadoop HDFS, Cloudera, Impala, and Apache Parquet, which is a columnar storage format. Yeah, well, after our evaluation, we found that for our requirements, the SQL on Hadoop option was the best fit. So how does this option look like? If you have a cluster of servers, we have a distributed file system called HDFS, which is distributed across all the nodes in the network in the cluster. On this file system, we store the DNS query data in the form of Parquet files, and these Parquet files can then be queried by the Impala query engine. Every node has a Impala daemon running, so if a user sends a SQL query to the cluster, the SQL query is distributed across all these Impala nodes, and the Impala nodes only process the Parquet data, which is local to the current node. So this avoids a lot of unnecessary network I/O, which improves the performance of the system. So for those of you who don't know anything about Hadoop or its components, I'll quickly go through HDFS. HDFS is one of the foundation blocks of Hadoop. It is the distributed file system, which has features like high availability through replication of data blocks. And it's scalable to hundreds of petabytes or thousands of machines. We don't have thousands of machines, but we probably never will. In theory, it's possible. So how does this work? Every file you store on HDFS is chopped up in different blocks, and every block is stored on multiple nodes in the system. It's sort of you can compare it to like software RAID. If one of the nodes with a block fails, there are other nodes available with replica blocks, and the data can be replicated to a new node if possible, if required. So Impala is technically not a part of Hadoop. It's a query engine made by Cloudera, which is a Hadoop vendor. It's what they call a massively parallel processing engine. And it's based on the Google Dremel paper. And its primary use case is that's to be used in low latency, high concurrency, BI analytical queries. Difference with the normal or the traditional Hadoop query engines is that the old Hadoop engines used more a batch-oriented way of querying data, which meant it was pretty slow. It had a lot of overhead in setting up the query, running the query, getting the results. So even small, simple queries took at least minutes to set up. With Impala, this is something running on Hadoop, but it's running on the same service as Hadoop, so it's running next to Hadoop, but it can use the functionality of Hadoop. It can read data from the HDFS file system. And it's written completely in C++ instead of the Java Hadoop stuff. So there are multiple formats you can use when running Impala, from text-based to binary-based. We use the Apache Parquet format, which is a columnar format. I'll discuss later. This is a very efficient format, especially for storing stuff like DNS data. Interaction with the Impala engine can be through a web-based GUI. It's very easy for an analyst to use the web-based GUI. You can just type in SQL, press a button, and get a result, and export it to whatever tool they want to analyze it in further. There are also command line interfaces like through the shell. You can use Python wrappers or JDBC if you want to go through Java. Well, I think this is the important part, I think. So why don't we use the PCAP files? Well, first of all, reading and compressing compressed PCAP files is just too slow. It takes a lot of I/O. You need to read the entire file to find the fields you want. And also, it takes a lot of CPU to decompress the gzip files. And there are no analytical engines that can natively use PCAP files as a data source. There is a Hive library from RIPE you can use to read PCAP files, but it's still batch-oriented. It's still slow. So we chose not to use that one. We chose to use the Apache Parquet format, which is a columnar storage format. So that it differs from the normal way databases store data on disk. Normally, if you have a data table with columns and rows, you store it row-oriented, which means that you store all the values of a single row sequentially on disk. If you switch to column-oriented format, this means that you store all the values of a column sequentially on disk. This means that the data is much more homogeneous, and that allows for better compression and the use of efficient encoding schemas. Well, so I already mentioned the encoding schema and compression. A good one is snappy compression. It's something made up by Google. It's a compression format that aims to be fast in compressing and decompressing, and aims also at reasonable compression. It doesn't have the compression ratio you get with gzip, but it's a lot faster and uses a lot less of CPU power to compress and decompress the data. We can use data partitioning. That means that you can create partitions for your data. You can store data by year, month, day, and server. And if you use query, if you use those partitions in your query, you say, oh, okay, I only want to use or query data from a single day or a date range. Then it knows which partitions to choose, and it can skip all the other partitions. So that will save you a lot of time in reading that data. And another cool feature is that if you store data in Parquet format, other analytical engines can also make use of this data. It's not just that you can use the data with Cloudera Impala. You can also use tools like Apache Spark and there are also other engines that can read Parquet data. So if you look at our architecture, oh, I need to speed up. You can see that there are four main components: the application service, platform, data sources, and the privacy framework. The data sources we have included right now are DNS data and ICMP data. We could add data from our sinkholes or registration system later on. Privacy is very important for us. In order to be able to comply with the Dutch Privacy Act, we have developed a DNS Big Data Privacy Framework, which integrates the legal, technical, and organizational aspects of privacy management. This is required because the IP address of resolvers may be personal identifiers. So every application that wants to make use of the data we have stored needs to create what we call a privacy policy. This privacy policy has elements such as its purpose, data that's to be used, what's to be used for, and stuff like that. This policy has to be approved by a privacy board at SIEN, which looks at the policy if it's acceptable, and if it is approved, then the policy can be implemented at the privacy, at the policy implement. Privacy. There are points in every component in the architecture where the policy can be implemented. I forgot the word. The current cluster setup we have is really tiny. It's only 5 nodes, 1 management node and 4 data nodes. The management node is also used for staging area before sending the Parquet data to the data nodes. The hardware is also pretty standard. Data nodes have 64 gigs of RAM and 6 terabytes of storage. This is also interesting. This is the workflow we have when getting data from the name server to Hadoop. What you see here is that the name server on the top left creates PCAP files every 5 minutes. These PCAP files are sent to a staging area where they are picked up by the PCAP decoder. The decoder decodes the PCAP into a memory format, tries to join the DNS request with the DNS response in order to come up with a single record. It does some filtering, removes some of the data we don't need, does enrichment. This means it looks up the AS number for the resolver IP, looks up the geolocation for the resolver IP, adds this to the information we already have. We also write out a lot of metrics about the data we analyze and how long it takes and stuff like that, which is available in our monitoring system. And finally, we write out the results as Parquet files and export it to Hadoop, where it's immediately available for analysis by an analyst. This is an example query where we count the number of queries from resolvers using IP version 4. And so we did this with a single thread and 10 threads, and we did it for a single day, 1 month of data, and 1 year of data. So if you look at the multi-threaded version, you can see that for a single day, it takes a few seconds. The scale is in minutes. So the day doesn't even show up, so it's less than 5 seconds, I believe. The month takes about, I think, less than a minute, and if we analyze the complete year, then it will take something in the order of 7 minutes. And you can take note that the data for the used to analyze the year is about over 2 terabytes of Parquet data, which roughly equates to 52 terabytes of compressed PCAP data. So for us, this is a pretty good performance. Status, currently we've hooked up 1 name server, getting about 150 million queries of that name server every day. In gzip PCAP format, that's about 33 gigs. If we convert it to Parquet, we are left with about 6 gigs. We have about 18 months of data in our database, which is about 71 billion queries with responses. And the volume is about 3 terabytes, and with HDFS replication that comes out at about 9 terabytes. And we estimate that the cluster capacity is somewhere in the neighborhood of 150 billion to 200 billion tuples. So these are use cases primarily focused on increasing the security and stability of .NL. We thought of things like visualizing DNS patterns, detecting botnet infections, real-time phishing detection, statistics, scientific research, for which we collaborate with Dutch universities, and operational support for our DNS operators. We have a couple of example applications. I'll try, if you have enough time, I'll go through 2 of them. One is the DNS security scoreboard, another is resolver reputation. This is our DNS security scoreboard, which we designed to visualize malicious activity. We do this by combining external phishing feeds with DNS data. And it works, this is the overall architecture. So we have got incoming external phishing feeds to an event analyzer. The analyzer gets the query data from a dupe, joins it with the event information, and saves it in the Postgres database. And you can look up the data through a UE. This is a screenshot of the UE, where you can see the information of the phishing attack visualized. At the top, you can see a chart with the number of queries per day for the phish. With the bars are the number of queries. And the red bar at the end is the day when the phish was reported to us. And as you can see, the days leading up to that event already showed an increase in traffic. So does the number of unique AS numbers and the geographical distribution of the phish. So these might be indicators that can be used for automated detection of malicious activity. Another application we designed was resolver reputation, which tries to detect malicious activity by assigning reputation scores to resolvers. It does this by fingerprinting. Yeah, I'll skip this. Yeah, we try to look at spam runs, botnets, and DNS amplification attacks. This is the architecture. Queries coming into our entire platform are being analyzed by the resolver servers through smart algorithms. As you can see, the resolver servers also use a privacy policy. If the resolver service finds anything interesting, at the moment it looks at botnets, and if it finds a botnet infection, it transmits the infection details to Abuse Hub, which is a Dutch initiative from SIEN and the largest Dutch ISPs, aimed at collecting abuse information and transmitting it to the abuse desks of the connected ISPs in order to be able to clean up the infection. So in conclusion, we found that Hadoop HDFS combined with Parquet and Impala is a very good combination. Gives us, even for our really small setup, gives us good performance and a lot of storage capacity. We made some contributions such as research done by our team and universities we collaborate with. We identified several malicious domain names and botnets, created an external data feed to our abuse information exchange with their Abuse Hub platform, and it gave us a lot more insight in the DNS query data we receive every day. So the future work is to combine data from our authoritative name servers with scans of the complete DNS, with DNS scans of the complete .NL zone, and even maybe data we get from our ISPs, which would be resolver data, to see if we can get a bigger picture because of caching and stuff like that, we're still missing a lot of data. And we also like to hook up more of our name servers and our resolvers and expand our open data program. Right now we have a statistics website, there's a screenshot here, which is our initial open data program. We would like to expand this with more data sets. I believe in time, okay. So if there are any questions, please let me know.
I was waiting for the applause for Martin. Okay, I'm relaying a couple of questions from the Java chat. So one from Bert Hubert. Is the Entrada code available somewhere?
Well, Entrada uses mainly open source components. Apache Package open source, and the Cloudera Impala stuff is also available for free if you don't want support. We changed as I mentioned, there is a RIPE library for decoding PCAP data for Hive, which is released on a LGPL, if I'm right. We modified that one in order to do the conversion to from PCAP to Parquet. That one is not released yet by us. I'm not sure if we will. I will need to check that. So if we were to release that one, then yeah, you could build this system for
Okay.
yourself,
The second question from Michael Eagles was related to the data model and the tool chain, but the tool chain is open source, mainly with some components here and there. So is the data model available?
Sorry?
The data model.
The data model. Well, the data model is pretty simple. It's like if you look at the DNS packet, that's the data model. So we just put all the fields of the data of the DNS packet, made them into columns, and that's your table.
All right.
So
Cool.
yeah, that's about it.
Andre Suri-Cizenek, I have a similar question. Do you plan to open source all of this for other registries to use?
This is right now it's a research project for SIDN Labs. So I'm not sure if we're going to open source this or what the plans are. So I can check that for you if you'd like, and can come back to you.
Yeah, certainly. I would like to. Well, since you build on open source components, and it makes sense.
Yeah. Okay. Thank you. Okay. Cool.
Thank you, Martin. Next up, we have magic going on. Next up, we have Zhaifeng, and I'm very sorry about the pronunciation of your name. I'm talking about long-tail domain clustering analysis.
Okay. Hi, everybody. I'm Zhang Zaifeng from Qihu 360. Today, I'm very glad to have a chance share some experience about cluster domains when we analyzing the DNS data, which based on our database. Okay, some brief information of our database. Our database is passive-dns.cn, which we are collecting the DNS traffic in China about 15% DNS traffic. Okay, last 30 months we had collected about 4.7 billion unique domains and 5.7 billion R sites and 17.4 billion R data. I think we are the first and biggest public database in China, and it had opened to security communities, include NSPsec and Ops Trust. Okay, today's agenda. First question, why we cluster domains? We hope to find some, we hope to understand the dizzy internet business from domain name. In other words, we believe that domain can reflect some internet business. Okay, we had lots of applications based on DNS, such as DNS tunnel, CDN domains, antivirus DNS blacklist, and DJ domains, broad prefetching, etc. But there are a huge number of domains which we didn't know what they are doing, such like the following domains. And there are many, and there are thousands of applications new emerged each day. I think the DNS data analyzing processing following those 3 steps. First, we use the unsupervised learning to process the unprocessed DNS raw data, and we get some cluster result. Under the manual intervention, use supervised learning methods to process the cluster result, and we get some rules. Use these rules, we construct some classifiers to process the DNS raw data, and we can get the classifier result. Okay, you can see the cluster domain is the first step of this process. Okay, from our database, we are collecting about 10 million new domains every day. I think it's a huge data. We can't process it totally. Fortunately, we don't care about the popular domains. What we cared, such as malicious domains and new business domains, are generally not popular. So focus on the long-tail domain is a good idea. We use the following rules to pick the domains. Last 7 days, active domains, second-level domain not in Alexa, top 500 sounds, and the first thing in last 3 months, and some other we had no DNS applications. Okay, we can compress the data site to 2 million per day from FQDN perspective. Okay, about clustering the domain, first thought is domain structure. We use the following 13 features to cluster the domain. And the algorithm is k-means. This is the result. You can see some clusters are accurate, but some are not so good. Why? I think there are some problems in domain structure cluster. First is feature adjusting is inefficiency. A big chunk of domains can be nicely classified, but the rest need lots of tweaking, feature adjusting. And domain structure is only one perspective. We need to consider other aspects, such as server IPs, client IPs, name servers, who is data. And the last is only domain structure missing the co-occurrence relations between domains. Okay, so we add 2 new dimensions, client IP addresses and domain IP addresses. Specifically speaking, we generate domain IP matrix and IP domain matrix. The latter is former's transpose matrix, and then calculate similarity matrix. We multiply the 2 matrix, and the third is calculate the pairwise domain similarity. And the last is using cluster algorithm to cluster the similar domains. There are some changes. There are some challenges. It's expensive calculation to calculate the domain pairwise similarity. Needless to say, we must compress the data size. Fortunately, we discard the single client domains don't affect the result. The compressed data scale is about 300 sounds per day. We calculate the similarity through Spark platform, and it can be finished in 1 hour. The cluster algorithm, we use Lowen method, which also performed on Spark platform. Okay, you can see the number of clusters. Client cluster average 45 sounds per day, and server cluster about 72 sounds per day. Okay, this picture shows the client, the cluster of client similarity in the red box. It's a configured DGA domains. If we zoom in the picture, you can see not all clients request all the generated domains. It's not a complete graph. Interesting. Okay, we also found some interesting findings. There are huge amount of non-existent government sites. I think it may be some type of scanner sends this strange request. Okay, the below domains is share similar server IPs and similar client IPs. They are online marketing application based on China's most popular app, which called WeChat. Use this method, we also found some DGA domains. Some of them has been checked by DGRQ, but some of them are unknown, which means they are not found yet to public. Okay, future works, we will add more dimensions, make the result more accurate, and we use this method to IP addresses. We will find the relationships between the IP addresses. Okay, that's all my presentation. Thank you for listening. Any questions?
Sorry. Hi, Martin Willink, SIEN. Okay. I missed it at the beginning, sorry. What's the data source you're using? Is this authoritative data or recursive data?
You mean data scale?
No, the data you use as input for your analysis. Where does it come from?
The long-tailed data about, okay, I found it. One calculates the similarity about 300,000 domains every day.
Oh yeah, sorry. I mean the actual raw data source
raw data source we are collecting about 15%.
Oh yeah, that's it. The passive.
Oh, okay.
So this passive DNS SIEN database, is that? Wait, how do you get? Is that also open for us if we would like to have access to it?
You can request a license.
Okay, who's running that? Who is behind passive DNS.cn? Is that CN, Nick, or?
No. Well, our company run it.
Oh, okay. Well, I'll find you later. And thank you.
Okay. Okay, thank you.
Thank you, Zhang. And last up, we have Sebastian Castro talking about something I should have memorized before coming over here. Publishing zone scan data using an open portal. Thanks.
Thank you, Sean. Okay, that's a long title for our presentation, but it's a short presentation. Hopefully you stay awake. Well, yeah, we're really close for lunch. Probably you're tired by now, but we keep it short and sweet. Kia ora, everyone. This is a short presentation about two pieces of work we put together. One is the SON scan for the .NZ domain namespace, and the second is the open data portal we launched recently, like a month ago or something. So NZRS, the company I work for, we run the .NZ registry and DNS infrastructure. We are an internet NZ company. Yeah, I have to put this there, so sorry. We are a provider of critical internet infrastructure, and we also authoritative for internet data. So we are starting this journey of embracing and encouraging the use of open data. We are trying to help not only New Zealand, but the internet research in general with, to provide arguments and discussion with real data rather than hand-waving. And we like to encourage the new generation of research, which is data mashups and visualizations and visual structure. So the SON scan, the first part of the presentation, we started in August 2013, and it runs monthly. We have a policy that governs the SON scan, which is available on that link, where we would describe where the SON scan will come from, what we do with the data, etc. So, and also one of the elements of the SON scan is the IP address we use. If you go and check it, sonscan.nzrs.net.nz will go to the policy page. So we try to keep things tidy and try to keep the network operators not jumpy about what we do. We are working based on a fork of DNS check from the Swedish. It's a fork because we use their configuration testing, but we also do the data gathering of mail servers, name servers, web servers, and all the stuff. So what kind of things we get from the SON scan? So the high-level notable examples are the domain is broken or not, does this domain has a name delegation or not, has a mail server, what are the status of the name servers as well, so do they answer UDP? You will say, well, what kind of name server doesn't answer for UDP? You will be surprised. How many name servers don't respond to TCP queries, how many allow recursion, how many allow SON transfers. And the SON transfers are the kind of tricky ones. It's the one we get most questions from. It's like, what are you doing with that data? Are you saving that data? So we have to go and put that in the policy. We do the check for DNSSEC. So the .NZ zone has been signed for 3 years, and I have DNSSEC envy with .nl because we have like 300 delegations or something like that. So it's not big. But we check for the signed domains, but also for the signed delegations. And I was surprised to see that .com has like certain number of signed delegations, so DS records in the registry, and then a higher number of signed domains if we have the same. We collect the web servers, mail servers, and name server addresses for both V4 and V6, so we can do the stuff that DIN is done for .ca, so mapping where are the servers. So we can actually compare nodes. We have the TTL distributions, so you'll see the TTL for name servers, web servers, and mail servers are not the same. They don't follow the same distribution, and it's really interesting. So we do that. We collect that data monthly. We save it in a database. We inject it into our Hadoop cluster, and we do some magic and produce some data. So this is like a pearl of stuff that some people will be really happy to see, which is we got approached by Microsoft New Zealand and saying, are you able to go and produce the number of domain names that are using our solution for mail? And we said, yes, we could do that, and that's the answer. So the main story here is you have to compare Google and Google Apps against Office 365 and see that in 1 year, Microsoft went from roughly 1% to 4% on domain names using the Office 365 for mail, compared to Google, which is on the top, in the range between 6 and 7. The rest are local providers that they park the domain and they specify a default mail server there, so there's nothing great in there. And while I was checking this data, we found out a cloud provider that says, oh, we are top leader in New Zealand. I won't say the name because that will be politically incorrect. But they say we are leaders in New Zealand, and they didn't make even under 0.5%. So it's like, okay, you can say whatever you want in your marketing. So what do we want to do in the future with this? So as soon as we have enough resources to take care of this, is collect data about new stuff. So the TLSA stuff that Shumon did is great. I really want to do that. Check out how many domain names have SPF there, the DKIM, any other things. Ed Lewis sent us an email when we did the launch of this, asking, do you have the key length for the DNS keys? And the answer was, sorry, no, we're using a very old version of DNS check. We will have it at some point. And because DNS check now transform into Zone Master, we might give it a try to Zone Master. Well, we'll see. So that's the collection. We collect this data, and I can make pre-graphs for you for web, JavaScript, I don't know, ggplot, whatever tool you decide to use, Excel. But it's not of much use other than my purpose of making presentations and going to lovely places to see lovely people, right? So we created this project. We call it the Internet Data Portal, idp.nz. We use a cloud solution provided by an American company called Socrata that allow us to publish this data. So we have aggregated data, we put it on their platform, and you can see the data, you can visually explore the data, and now the Google Analytics for the website is exploding because everyone is typing idp.nz. So we have 2 data sets we produce, and we also have 2 data sets that comes from Statistics New Zealand. So the data sets we produce are the .nz Zone Scan I just explained, and some aggregated numbers about the registration data for .nz. Those are aggregated and anonymized, so they are safe to use. So the main URL, so we're entering into the URL realm now, and do you want to allow that? Yeah, okay, allow this. Okay, someone change the URL. Sebastian, you need to update the, so this is a Internet Data Portal. This is a Zone Scan. And that's the data. So are you really ready to visually explore this data? Oh, definitely. So you see we have counts of domain names, count of name servers, domain errors, the description of the error, and a count. And there are like 900 entries per Zone Scan, and there are 2 years of Zone Scan. So it's not a small data set, but not either a large data set. So my presentation. So the Visual Explorer, the URL for the Visual Explorer is here, where you can actually go and query stuff. So when did it started? You can go and, I want to see all the data for March. And then the graph on the bottom will update immediately, showing you stuff. So that's automatic, right? That's what the tool provides. It's not a really perfect suit for this kind of data set, but for the other data set, it's really, really nice. So domain name level errors. So this is a timeline of error for domain names. And you see, we can actually scroll here and see, move around how many domain names have a missing glue, how many domain names have only name server in one ASN. The short answer is roughly 50%. So I was like, no, you had to be kidding. 50%? Yeah, it's 50%. I'm not proud of that. Etc. You can actually go and explore what are the numbers, and if you want to download the data, you have a link here with, do you want this as a CVS? There you get it. Do you want it as a JSON? There you have a link. And so the possibilities are limitless. So name server errors. So how many name servers support NSID? How many name servers don't answer to TCP queries? Do you see the number? And if you actually extend the time scale here, you can see an increase in the last few months, etc. So you can actually go and play for hours with the data. DNSSEC status, so this is where the guys from SIDN laugh. Number of signed domains is between 250 and 300. But the number of domain names, which is the yellow line with DS record in the registry, is actually flat. So you see there's like 1-2 difference there. The reason is registrars that don't support DS records. IPv6 adoption doesn't look that pretty. Yeah, I won't be there because I'm running short of time, but DNS key algorithms, this is the count of DNS keys. You see the ramp up of the SHA 256, the appearance of the SHA 512 at some point in April 2014, and the rest is flat. This one is a really interesting data set. This is the TTL distribution. So this is only from a sample because you cannot produce like a bar chart with timeline. That doesn't exist yet. But we use TTL buckets, and I'm showing you the TTLs for mail servers, name servers, and web servers. So which one is the most common TTL for name servers? An hour. But also you have that for web servers. It's like, what? That, again, is strange. And you see there's a long tail, and then between name servers, 24 hours. And this is really fun to do. And you can actually do this on your own with the data. So what are the potential uses for this? So this is where I got, OK, I can go and mash up this together with a bunch of stuff. So let's do geolocation for servers. Yeah, allow me to go and show. So this is our general blog of where we do stuff, and this one has 3 different maps. So the first map, when it finishes loading, is kind of a dashboard. So you can actually go and explore for a given date. For a given date, what is the distribution of mail servers per country? So the scale is between 1 and 49%. Mainly in the United States, Canada 1%, Australia 11%, 49%. So 50% of the domain names have mail servers in the country, and a few in Europe. So what about name servers? Slightly different, 55 in New Zealand, 24 in Australia, etc. OK, that's a dashboard you can play along. Using the data, we can go and put it directly in Python and use Plotly and generate this graph, which is embedded, is interactive, etc. And finally, using D3, we can do an animation where it's showing, so it's running at the moment, but the changes, there are mainly no changes in there. So you can stare at the there was a change in there, but it's not major. But the possibility is there. The data is available. We download the data directly from the portal. We put it on this visualization, and it's done. So for the future, we want to add more data sets. We want to add DNS traffic to this. Geoff Houston wanted to share his DNSSEC and IPv6 adoption numbers from their experiments. We might add it to there. We want to add some string analysis of the registry, so how many domains are to 1 or 2 metric distance using Levenstein, calculating portfolios, so how many registrants has how many domains, do word segmentation and word tagging. So for example, how many domains have a geographic location on their name and stuff like that. And using external visualizations with the data. So that's the end of the presentation. I invite you to go and check the site, play with the data, and you can actually use it to compare, oh yeah, we've been doing this for our TLD. We can now compare with .NZ and see how it goes. Thank you, that's all for me.
Hi, Sebastian. I have one question that came from the Jabber room from Michael Eagles for you, which is whether the scanning can be extended to look at data beyond .nz.
Any suggestion of what kind of data?
Not that I saw in the room, no.
Okay. Well, I can ask Michael because so the tools we use is open source, and the code we use is in GitHub. So there's nothing specific about .nz on this data collection. It's like, yeah, we use it for that, but anyone can replicate it. All right, lunchtime? Yes. Okay, thank you very much for your attention. Sean?
Thank you, Sebastian. That was the last presentation of this session. I think Keith has a couple of words to say before we break for lunch. Keith? Maybe?
Okay, so we're breaking for lunch until 2 p.m. Again, we are extremely well on time. So lunch is upstairs. As I say, make sure you remember your badge because we're going to have to bounce any nano people who are trying to eat your lunch. We have a survey now available. So Dave, can you queue up the rolling slide? We'd love to hear what you think about the workshop, about the content, about the logistics, so that we can improve for next time. So if you could all have a go at completing the survey, that would be very much appreciated. It's in there somewhere. And really, I'd also just like to thank our sponsors, Sarah and Nominum, for helping pay for the nice lunch you're about to enjoy. If you need to leave before the end, it would be great if you could hand back your badge holders and lanyards, and indeed if you have any voting cards left from yesterday. So that's basically it. We'll be back at 2.